Here we are in Lesson 7, Unit 6. We're looking at integration by substitution today. The biggest idea for integration by substitution is we need to find a piece of the function whose derivative is also in the function. I can't stress that enough. Maybe it could be off by a constant, but that's what we're looking for. Here's a procedure for you here. Look for a piece of the function whose derivative is in the function. Set u equal to that piece. Use your u and your du to replace parts of the original function. And we'll tackle a few of those here. So 3 simple things. Here's that procedure again, written symbolically. And here's that procedure again, written symbolically a different way. If I can see a composition function, some outside function and an inside function, and the derivative of the inside function is in the integral, then we can use U-substitution. Now, if you've never seen that before, that seems a little confusing. So trying and doing is probably the best bet here. So we have several on the first example. I think there's 6 of them. Integrate by U-substitution. So we're looking for a piece of the derivative in the function. So I see that the function x squared plus 1 has a derivative of 2x. I'm calling u my x squared plus 1 because the derivative du with respect to x is 2x dx. Now it's just a matter of matching up the parts. Get a highlighter here. The parts in the original problem. You see the 2x dx can be replaced by du, and then the x squared plus 1 can be replaced by u. So there's substitutes, U-substitution, which gives us the antiderivative. Whoop, let's go to blue. This gives us the antiderivative of u squared du. And I guess really I need to kind of erase this because that's not part of my u. Okay, so if I antiderive u squared, we're going to get 1/3 u cubed plus a constant. But then we have to back substitute because u was x squared plus 1 and replace that here. Our general antiderivative, x squared plus 1 to the 3rd power plus a constant, would be U-substitution for that function. Okay, let's give this one a try. My u is going to be the inside piece, this argument 4x. Since the derivative of 4x is 4 dx, we can replace the 4 here and the dx here with du, and we can replace the 4x for the cosine argument as cosine of u. Antiderive sine u plus a constant, back substitute, 4x takes the place of u. So the sine of 4x plus a constant is our antiderivative, the general antiderivative, the indefinite integral. Moving on to part C, the 4x squared plus 1 would be a good U-substitute since the derivative is 8x with respect to x. 8x with respect to x is the replacement. So we've got the square root of u, and du takes care of everything except the radical. So integrating the square root, we have u to the 3/2 times 2/3 plus a constant. Go back and grab your u and interchange that substitute. So we have 4x squared plus 1 was our u, and the antiderivative gave us 3/2 power plus a constant. Indefinite integration by U-substitution. Not so bad. Most of them are just nested inside. You're looking for the ugliest part. Give that a try. If that doesn't work, try something else. So here's our first one that's off by a constant. So I don't have inside the integrand, I don't have a 2x there. We could get rid of the 2x to create x dx, because that is what we have, x dx. So in this sense, I'm going to take the x squared plus 3 quantity cubed and the x dx, and here's what's happening with that. Just rewrote it so you could see. So where the x squared plus 3, oh, where did that come from? Back that up. X squared plus 2 is the u. So we're dropping a u in here, u cubed, and the x dx now needs a half du. So we can put the half out here and the du there. Now integrate for the indefinite integral. So u cubed, it becomes u to the 4th. We're dividing by 4 and adding the constant, which gives us 1/8 of u to the 4th. But remember, u was x squared plus 2. And that quantity was to the 4th power plus a constant. So even if we're off by a constant, we just balance it out and replace what we do have with that balanced out expression. That's part D. 2 more on this example. Part E, in this case, it's usually something in the ugliest part. In this case, it's in the denominator. If we use the denominator, 4x squared plus 3 as our u, the derivative is 8x dx. Don't have an 8 up here, so we can kill it with an 8 that way. See how I'm balancing that out? I give it what it doesn't have and then balance it with an inverse out in front. So I have an x dx. Let me erase this. Okay, so we're integrating. 1/8 goes out here. The du can stay inside, so I'm replacing 1/8 du with the x dx. And we have a u on the bottom, so the power is -6. Find the antiderivative for u to the -6. Adding 1 makes u to the -5, and dividing by -5, or multiplying by -1/5, plus a constant gives us -1/40. And what was u? 4x squared plus 3 to the -5th power. So what does that look like? Either that or -1 divided by 40 times 4x squared plus 3 to the 5th power plus a constant. Either that one or that one. Just depends on what you prefer. Now our last one. And once again, we're looking for the ugliest part of the integrand, which would be under the radical 7 minus 2x cubed. Our derivative needs to be a squared term, and I see that right there. So the derivative of u is du dx, and this derivative is -6x squared dx. Don't have a -6 in here, so we'll divide by -6, and replace x squared dx with negative 1/6. Again, if your brain sees that we could also include a negative 6 in here, then you could kill and counterbalance with a negative 1/6 out to here. So I gave it what it needed, and I balanced it with its inverse operation, whichever way your brain processes it. So we're integrating. Whoop, nope, let's go to blue. Integrating, we have this u value, that's to the 4/3 power. We need negative 1/6 du, so we can integrate with respect to u. And the antiderivative for u to the 4/3, we're adding 1 to 4/3 and multiplying by the reciprocal, 3/7, plus a constant. Then 3 divides 6 2 times, and we end up with negative 1/14 u, which was 7 minus 2x cubed from here to the 7/3 power plus a constant. So that's not so bad. Example 2. Some clever trig identities and algebraic methods will rename functions, and then we can use U-substitution to integrate. In these, we're actually discovering some set rules. So let's say we rewrote tangent as the quotient of sine divided by cosine. So watch this, remember this carefully. If you ever get stuck on an AP exam or a test, you can always go back and reinvent the wheel here. The U-substitute would be our denominator, cosine. I said denominator, I'm starting to write numerator. Our denominator. The derivative of cosine is negative sine. The only thing we don't have is a negative, so that could easily be taken care of. Put the negative outside, and we have a u to the negative 1 with the du. Now, several days ago, lessons ago, we had the integral du over u is natural log of the absolute value. So I believe that was in the properties lesson when we had the list of all the derivatives and all the integrals for the year. This is one that you're going to want to memorize. So u to the negative 1 is a u in the denominator. That gives us the natural log of absolute value of u plus a constant. And our u is cosine. So natural log, the absolute value, excuse me, cosine x plus a constant. And you can memorize that or reinvent it each time. Now, can you do that with cotangent as well? Cotangent's the same as tangent, only different. In this case, we have sine in the denominator. Let's make that look like a better x than what I did, dx. So if we use sine for our u, then sine's derivative is cosine. That's our numerator. And following along in that same thing, we have 1 over u, just writing it different than this. So natural log of u was sine, natural log of sine of x, absolute value, plus a constant. So cotangent ended up with a positive answer, tangent with a negative answer. And you'll see those kind of trends all through. So how about secant? Secant's a little testy. So we're going to perform some math magic here. You know, the derivative for secant is secant plus tangent. So let's try this. I can multiply top and bottom. Oop, need an eraser. I can multiply the secant of x by secant plus tangent. You wouldn't normally know to do this. I'm just planting that seed in your head so you can kind of think outside of the box a little bit. Sometimes those identities help. Now, if we distribute secant to the numerator, we'll have secant squared plus secant tangent divided by secant plus tangent. And then we can use some ideas for denominator, secant plus tangent. The derivative of secant is secant times tangent. And the derivative of tangent is secant squared. That's magic, because this line is our numerator, and this line is our denominator. So a little bit of math magic, which gives us du over u, which is also the natural log of absolute value of u, and here was our u. So our final answer is natural log secant x plus tangent x, absolute value plus a constant. So that's one I wouldn't want to memorize, but there's the antiderivative for secant. Then cosecant is pretty much the same thing. We have cosecant x here. We're going to multiply by cosecant plus cotangent. I wrote cosecant plus cotangent on the top and the bottom. Well, my pencil is ahead of my brain today. Cosecant plus cotangent dx. And then expanding that would give us cosecant squared plus cosecant cotangent, which is the derivative that we would look for. And on the bottom would be cosecant plus cotangent in terms of x. So same deal. If we use the denominator as our u, then the derivative of the denominator is negative cosecant squared x, and the derivative of cotangent is negative cosecant cotangent. In terms of x, take that negative out and end up with 1 over u du, because see, pulling this negative out is going to give us the numerator. And then same as before, just negative here. We have negative natural log of u, and u was cosecant plus cotangent, absolute value plus a constant. So trig ones are a little triggy, but they're doable. In this case, you could use one of the double angle formulas for sine squared. So thinking about sine squared x is 1 minus cosine 2x divided by 2. And in that case, I can use that double angle formula, or that's a power reducing formula, and do 1/2 of the dx. So I'm splitting up the fraction, minus 1/2 of cosine 2x. And then in this case, this is the piece we're going to use for a U substitute, since in this part U could be 2x. The derivative of 2x is 2. And we don't have a 2, so we'll divide by a half and pick up from there. Okay? So in this piece, it's very simple. I just have 1/2 x, and then we have a negative 1/2, or subtract a half. We need another half out there for this part. And the cosine of our u, so the u was 2x, putting a u in there and integrating with respect to u. 1/2 x minus 1/4 sine. Sine's derivative is positive cosine, so we keep this minus out here. And sine of u was 2x plus a constant of integration. So 1/2 x minus 1/4 sine 2x plus a constant. And then in this case, we've got, maybe expand that out and let's see where that goes. First, I'm going to shrink this up a little bit. Okay, my writing was too big. Now, in this case, we're going to expand the binomial for sine squared plus 2 sine cosine plus cosine squared. And by doing that, you see sine squared plus cosine squared equals 1. So we add those two together and use that identity. And 1 plus 2 sine x cosine x becomes more manageable. So in this particular case, we'll do as the other one. We'll separate the two and use sine for my u, because cosine is the du. And then we can use these for U substitution in the second part. So integrating 1 with respect to x and integrating 2 u du will give us what we need. So 1 dx is x, and 2 u, we're going to add 1 to u, that's going to be u squared, and divide by 2, and u was sine plus a constant, which gives us a final answer of x plus sine squared x plus c. So they're a little tricky, but if you're careful, you can handle this. Now, this next section or topic is how we can change the limits of integration when we're solving for definite integrals. Because each term, each integral is in terms of x, and we're going to change the upper and the lower bounds to match our u substitute when we switch over to u variables. In this example, if we use u as tangent, you can see that the derivative of tangent is secant squared. That's the little piece that's hiding in my problem. I'm looking for the derivative in the problem because we don't have a way to multiply. There's no multiplication rule for antiderivatives. Now, here's the tricky part. This is when x equals 0. When x equals 0, u is the tangent of 0. So u is 0 because the tangent of 0 is 0. This is when x equals pi over 4. When x is pi over 4, what is u? U is the tangent of pi over 4. In this case, u is 1. So this is my new lower bound, 0. And this is our new upper bound, 1. We want to take care that we're paying attention to that. This is when u is 1 and when u is 0. This was for x. So our antiderivative is going to be u times du, since we already had secant squared dx. That's our du. Okay, we're going to leave everything in terms of u. Never go back to tangent or secant, 0 or pi over 4. We're going to use this new upper bound and new lower bound. So anti-deriving u would be 1/2 u squared as u goes from 0 to 1. So we could use the 1/2 outside and then square 1 and square 0. And our antiderivative definite integral is 1/2 times 1, or 1/2 in this case. Okay, fairly straightforward, just have to be really careful. Same thing here. Let's try the denominator. I'm going to leave the cube alone and just let the u be the cosine of 2 theta. Using the chain rule, the derivative of cosine 2 theta is -2 sine 2 theta d theta. So we got the chain rule. The derivative of cosine is negative sine. The derivative of 2 theta is 2. Don't have a half over here. We'll divide by -2 and have sine 2 theta d theta. There's my numerator. We're replacing it here. But don't forget your variables. When x is 0, u is cosine 2 times 0. What's u? When x is pi over 6, u is cosine of 2 times pi over 6, or cosine of pi over 3, and cosine of pi over 3 is 1/2. Okay, so we have our new lower bound and upper bound. When x is 0, u is 1. When x is pi over 6, u is 1/2. We got a problem here. We're going to have to switch that. But let's take care of this. Sine of 2 theta is du. And on the bottom, cosine, we had cosine cubed. On the bottom, we got cosine cubed, right? But our limits are wrong, so we have to switch them around and make this negative go from 1/2 to 1 this way, and we have u to the -3 du. So take the antiderivative, keep all of the u's, don't go back to the x's, and we'll balance it out that way. So adding 1 to -3 gives us -2, and we're dividing by -2. Okay. Evaluating from 1 to 1/2. So let's take this half outside with this other negative, which would give us a positive 1/2. And then substituting 1 over 1 squared minus 1 over 1/2 squared. So we have 1/2 times 1, and then this becomes 2 squared, or 1/4 squared, 1/4, which is 4. So that's going to be -3 over 2, -3 over 2. Let's make sure I didn't make a mistake there. Oh yes, back here I did make a mistake. I forgot my 1/2 right here. That's supposed to be let's back this up. So we need this negative 1/2 out here. So there's still a negative 1/2 out here. And that negative 1/2 and this negative 1/2 now becomes 1/4. Got to watch the arithmetic. Let's see. Clean this up a minute. Now my substitute is back. Let's see. Go all the way back. So this piece here should have the negative 1/2. And then we flipped the intervals around, so the negative became positive now, because a negative makes this positive. This is positive. That's negative 1/4. Erase this. And a negative 3 and a negative 4 makes a positive 3/4. So a negative 1/4 times a negative 3 makes a positive. Ooh, all of that arithmetic. We can do calculus, just can't add and subtract. In example 3, let's call U the radicand, 1 plus x cubed. Then du is 3x squared dx. Pretty straightforward. When x is 0, placing a 0 here, u is 1. Then when x is 2, placing a 2 here, that's 8 plus 1, u is 9. So lower bound, upper bound in terms of u. The new lower bound is 1. The new upper bound is 9. And we have the square root of u in terms of u, which is u to the 3/2 times 2/3, evaluated from 1 to 9. Pull the constant out in the front, and 9 to the 3/2 minus 1 to the 3/2. The square root of 9 is 3. 3 cubed is 27. This becomes 1. 27 minus 1 times 2/3 would be 26 times 2. 26 times 2 is 52/3. One more. So same thing, they're pretty much straightforward. 1 plus 5x squared, du is 10x. We're off by a constant by a factor of 10 to get our numerator. When x is 0, u is 1. When x is 1, u is 6. So new lower bounds and upper bounds. 1 on the bottom, 6 on the top. And we're integrating u to the negative 1, which is natural log. And we're off by a tenth. So 1/10 natural log of u. We're evaluating from 1 to 6, which gives us 1/10 natural log of 6 minus natural log of 1, but natural log of 1 is 0, and our definite integral is 1/10 natural log of 6. So we don't need absolute value bars since 6 is a positive number. Okay, then the last section, the last set of examples, using long division. This is something I would expect on the AP exam. It's something new. So we can rewrite things using long division to integrate. If you remember your long division, I'm going to use synthetic division here. because I have reducing powers on x, 3, and a binomial whose coefficient is 1, so that makes it really simple. Remember, the rule is to bring down the first term and multiply, then add, multiply, then add, multiply, then add. So no remainder, that's really good. And then I can reduce this down as x squared plus 2x minus 3. We don't have any remainder to take care of. We've divided out. And the reduced polynomial, or depressed polynomial, makes it very simple to integrate. 1/3 x cubed plus x squared minus 3x plus a constant. So using long division, we can integrate. Let's try one more. In this case, I'm kind of forced to use long division. We have x squared plus no x term minus 4. And x squared divides x squared one time. 1 times x squared plus 1 is here. I want to subtract. So this is gone. And our remainder is 5. Now that's a little bit of an issue because it's over this denominator, right? So our quotient is 1, but our remainder is -5 over the divisor. And integrating 1 is just x, but integrating 5 with 1 over x squared plus 1, this is the inverse tangent. So 5 inverse tangent of x. So let's just make a note of this down at the bottom. Remember, the derivative of tangent inverse x is 1 over x squared plus 1. So you have a little recall there. Okay? Last example. Complete the square. So we can think of the denominator as a binomial squared. So if you see that you have a complete square on the bottom, your u would be x minus 4, and du would be just 1 dx. That would make our integral 5u to the -2 add 1 to -2 and divide by -1. Antiderivative is 1 over x minus 4 to the first power plus a constant. One more example. In this case, it's not a complete square, so we're going to regroup. Let's say we're going to regroup as a perfect square. So to regroup as a perfect square, 3 would be in our numerator, and x squared plus 2x, half of 2 is 1, 1 squared is 1, but we're going to keep it balanced and subtract a 1. This is what I'm talking about by regrouping. And then that 2, I just moved it outside. So to simplify that a little bit, it would look like 3 divided by x plus 1 squared, and 2 minus 1 is 1. And in this case, I see in my mind's eye the tangent inverse, because tangent is a squared plus 1, or x squared plus 1. So I'm thinking about this rule. again, I'm pulling all these rules from the lesson that had all the properties and a page full of rules. So if our u is x plus 1, we'll call u the x plus 1. Then a is the 1 to follow this pattern. And our integral would be 3 tan inverse of x plus 1 plus a constant. And the 3, we just pulled the 3 out here, which is this 3, our 1 over a, and tan inverse of u over a is where this came about. So one more lesson to go, and we'll be finished with chapter 6 or unit 6.